Welcome to our second session in thermodynamics. Um, Welcome to our session in thermodynamics, and I hope that it shall be very interactive as usual. So, as a way of introduction, let me start by looking at uh, looking at our course outline. So generally, we are hoping that in about 10 weeks, we should be done with the course content, and that you are going to be able to explain the fundamentals of thermodynamics, the properties of pure substance and their mixtures. You shall be able to apply the laws of thermodynamics and be able to analyze energy flows in a variety of systems, and you are going to be able to use properties defined by the first and second laws to analyze thermodynamic cycles and explain Gibbs free energy and describe obtainable work from engineering and biological systems, and use equilibrium processes to explain cellular thermodynamic reactions. Okay, so definitely understanding of engineering mathematics. I think you know if mathematics for technologies, which is HIT 113, I suppose it should make it easier for you to grasp the mathematical concepts in this particular course. All right, so in terms of our assessment, the assignments shall contribute 15% and the tests will contribute 10%, which makes 25% for the continuous assessment, and the final examination would constitute 75%. All right, and like I said, I have divided the course content into 5 different chapters, where chapter 1 will be more of introductory, with introductory concepts and definitions, as we look at the scope of thermodynamics, dimensions and units, measures of amount and their size, thermodynamic system and control volume, properties and state of substance, processes and cycles, force, temperature, pressure, equilibrium, the Zeroth law of thermodynamics, energy, work, and heat. And so accordingly, uh, in a nutshell, um, this will be the general presentation, which I've tried to include all of these. But you'll notice that the way we understand thermodynamics, or each and every concept, varies from one person to the other. And so I've tried to ensure that in terms of our reference readings, we have different types of textbooks, such as Chemical Engineering Thermodynamics, 6th edition by J. Smith, and also Fundamentals of Engineering Thermodynamics by Michael Moran. You may also read Biochemistry by C.K. Matthews, or Biological Thermodynamics by Heine. And so, for example, here is Chemical Thermodynamics, Basic Concepts and Methods by Ivan M. Klotz and Robert M. Rosenberg. I have about 1, 2, 3, 4, 5, 6, and 7 different textbooks on thermodynamics, which I'm going to share with you on Google Classroom for your further consumption. So this is chemical thermodynamics, basics, concepts, and methods. And thermodynamics being thermodynamics, whether you apply it in relation to chemical or to biological terms, it remains thermodynamics. When we are applying it in the biological area, we call it biophysics. But the laws doesn't change, the law remain the same, and different areas of application also remain the same. But we'll try to filter the depth so that it remains applicable and relevant to our biological field. Okay, in that regard, it means that we are going to look at the different quantities, extensive and intensive quantities, different measurements, and the like. Okay. We also have another book, Fundamentals of Engineering Thermodynamics, by Michael J. Moran. Like I said earlier on, it's also good for you and easier to understand as you go through it. You quickly understand different concepts and be able to relate with the area of thermodynamics. So it makes it actually makes life easier for you as you go through this particular textbook. It takes you from the very basics, and you can easily relate on thermodynamic applications with relate to biology, to the biology world, to the industrial world, and so on. Okay. Um, so this textbook is also good for you to understand in depth what I've summarized in the PowerPoint presentation. When we talk of extensive and intensive properties, what do we mean when we are talking of an extensive property? What do we mean when we talk of an intensive property? And so on. So you also need to acclimatize yourself with different SI units for each of these dimensions, which include mass, length, time, and force. And it is equally important in your applying this thermodynamics in the physical life. We shall also get to understand about pressure. How do we calculate pressure? And the like, and it is equally important in terms of temperature. How do we calculate temperature? What are the differences between thermometers and the like, and the different measurements in terms of the temperature readings, and so on. Okay, so first things first. Okay, so this was one of the textbooks. We also have got another textbook, which is Fun Introduction to Thermodynamics and Heat Transfer. This one I also find it very easier for one to grasp through the concepts and even the narration, which will enable you to really understand uh, what is thermodynamics and how do you navigate your way to understand the different concepts that are raised as we go through thermodynamics. So basically, when we talk about applications of thermodynamics, like I said, you can apply them to the human body, to the air conditioning systems, to aeroplanes, to refrigeration systems, to power plants, to automobile radiators, or even car batteries themselves. And uh, these textbooks are also visual in that they give you some diagrams to make it easier and enjoyable to go through these particular textbooks. So I hope that we are going to have a good time as we go through this. So, okay, like I said, um, these are the applications, and our dimensions can be primary or secondary, with units being in the SI, that is International System or English System. And uh, International System for length is meters, for English System is feet. In terms of time, seconds across the board. For mass, the International System has got kilograms as the unit of measure, but in the English unit we have pounds, which is lbm here. So mass is measured in pounds there, and so do the rest of the dimensions. As you compare, you'll be seeing the respective dimensions and units. Okay. And in terms of measurements and also dimensions, again, if you are to look in multiples of 10, 10 to the power 12 is tera, 10 to the power 9 is giga, to the power 6 is mega, to the power minus 6 is micro, to the power minus 9 is nano, and the pico level is 10 to the power minus 12. So why are these dimensions and units important? They're important in the day-to-day measurement and applications to real life. Say, for example, we are looking at trying to ascertain the thermal stability of a particular enzyme. We do molecular dynamic simulation study. And if you are simulating this on a computer, we are trying to measure at what nanoseconds or at what nano level will be our enzyme of interest remain stable. So these measurements and dimensions and units are very important for us to relate, so that as we apply them in real life scenarios, we really appreciate them and we move in the same at the same pace. Okay, so every thermodynamic system, or simply every system, is defined as a quantity of matter, or generally a region in space which we have chosen for study, and the region outside that system is what we call the surroundings, and the real or imaginary surface that separates the system from its surrounding is what we call the boundary. Okay, and so this is the illustration. Any other thing which is outside the system becomes the surrounding, and what demarcates the surrounding from the system is the boundary. Okay, and so if the system has a fixed mass, it is called a closed system or control mass. So only energy is able to cross through the system boundaries. Okay, and this is the scenario where you can have energy passing through across the closed system boundary, or across the in and out of the closed system, but you cannot transfer mass of a system in and out of the system. Okay. We also have what we call an open system or control volume. And so in this case, this allows both the mass and the energy to move in and out of the system. Then we have what we call an isolated system, which is a general system of fixed mass where no heat or work may cross the boundary. And in this case, we are saying it is isolated because both the mass and the energy cannot pass from or into or out of the system. Okay, right, so we shall look into detail when we look at heat transfer concepts and mechanisms to appreciate this aspect of open system, isolated system, and closed system. Right, but it's also equally important for us to understand and appreciate the different properties of a system. These can be macroscopic, these are actually macroscopic characteristics of a system, and we call them properties. So a property, these include pressure, temperature, volume, mass, density, energy, enthalpy, entropy, and so on. And these properties can be dependent on the mass of a system, or they may not be independent. They can be extensive properties, or they can be intensive properties. Okay, right. So if you are to look at extensive properties, these include specific volume, which is calculated as volume over mass. We also have specific total energy, specific internal energy, specific enthalpy, and specific entropy. Okay, right. So that's it for the properties of a system. We shall later look at this maybe in another lecture, where we are going to calculate the specific volume, calculate the specific enthalpy, calculate the specific entropy for each of these. Okay. And then moving on, we've got state and equilibrium. We shall look at state and equilibrium. In this case, we see a system at two different states, state 1 and state 2. you can note the difference that there, that it is mainly in the area of volume. The volume in the first state is different from the volume in the second state. What has happened, we need to look at it from the point of uh, a, a equilibrium and non-equilibrium factors. Okay, so basically, if you are saying a system is in a thermodynamic equilibrium, uh, that system should have four things in common, or four different types of equilibrium coming together. The first one is thermal equilibrium. In other words, the temperature should be the same throughout the entire system. Secondly, the pressure in that particular system should be constant. And hence we say, when it is constant, we are saying that the system is in mechanical equilibrium. Again, if the mass of each phase in a system reaches an equilibrium level and remains there, we say the system is in phase equilibrium. And if the chemical composition does not change with time, we're simply saying the system is in chemical equilibrium. All right. So if we take a look at a closed system which is reaching thermal equilibrium, before there was 20 degrees Celsius, 23, 30, 35, 40, and 42. And when it reached thermal equilibrium, in diagram B there, we see that the temperature throughout the system was at 32 degrees Celsius. Okay. Now, if you are to proceed further, as you look at the state postulate, you notice that the state of a simple compressible system, which means every system is capable of compression, it can be compressed. So the state of a simple compressible system is completely specified by two independent intensive properties. Okay, and so the state of nitrogen, for example, is fixed by two independent intensive properties, which are temperature and specific volume. So specific volume is small letter v, and is written in this manner. And whereas volume will be capital letter V. So take note of the difference. The temperature is 25 degrees Celsius and the specific volume is 0.9 cubic meters per kg. Why are we saying it's specific volume? It means that this volume is dependent on the mass of the system. So if you are measuring the volume per kg, this becomes the specific volume for us. So how we calculate it may seem to be similar to how we calculate density, because generally density is mass over volume. And so you may note that the measurements, the unit measurement for specific volume and density are like the same. Okay. Now, you also need to appreciate that in thermodynamics, we've got processes and cycles. And so any change that a system undergoes from one equilibrium state to another is called a process. And so when a process proceeds in such a manner that the system remains infinitesimally close to an equilibrium state at all times, that a process is known as a quasi-static or quasi-equilibrium process, as you can see in this diagram. So like I said, when a process continues in that manner, where it remains close to an equilibrium state, at all times we say it is a quasi process or a quasi equilibrium that is taking place there. Okay, if I may proceed. You also
Say, can you please have further clarification on that quasi-equilibrium?
okay. Can you please come again?
I said, can we please have further clarification on that quasi-equilibrium?
Okay, further clarification.
Yes.
All right. So in this case, where we are saying that in this case, looking at this example, for example, the incremental masses are removed during an expansion of the gas or liquid. So what will be happening is that uh, as the system is moving from one equilibrium state to another, we are saying that that is a process, right? But when that process continues in a manner that the system remains close to an equilibrium state at all times, either it is moving from solid to liquid, and or it is like we are saying it's an expansion of a liquid or a gas. As it expands, there is a shift that is taking place, uh, and as it continues to expand and it remains at equilibrium, it means that there is little variation to what is happening to the process, because in this case it is the gas or the liquid that is expanding. So say for example, in this particular scenario, we are having a gas which is expanding. So if it is expanding, it is expanding at a constant process, which means what is increasing really here is the volume. So the volume of a gas is increasing as pressure builds against either it's a lid or it's any clothing that will be there. As the liquid or as the gas expands, and that process happens at a constant level, it means that uh, it remains in an equilibrium state. What we call this process, we call it a quasi process or a quasi equilibrium, because if you are to look at the nature, remember I said a system can be in mechanical equilibrium, which means the pressure is constant. Uh, but when the pressure begins to decrease, but the rate at which it is decreasing is so slow to that as it shifts to a level where the volume of the system is increasing, but the volume of this system as it increases, the both the pressure remains constant. We are saying that process that is happening is a quasi process or a quasi equilibrium, because you cannot really tell the difference whether there is really a change in pressure. But what you really note is a change in the volume of the system. Like in this case, the gas in a container is expanding, but the rate at which it is expanding, it's in such a way that there are very little to minor, there are little to almost no changes that are realized, because it is happening gradually to a scenario where the system overall remains close to the equilibrium itself. Am I clear?
Yes, sir.
All right. So I can
mpaka
proceed.
yupo.
All right. As you read, as you go through the textbooks, you understand this much clearer. It's just that for now, I'm just generalizing. But when you look at different scenarios and setups, you'll begin to appreciate that this is an example of a quasi process or a quasi equilibrium. Okay. All right. So I think there's someone who's trying to join. Okay. All right. I can see Precious, you're still raising your hand. But anyway, let me proceed. Okay. So now moving on, processes and cycles. Generally speaking, you note that the state of a system can move if we are speaking, say, concerning volume in its relation to pressure. The state of a system can move from state 1 to state 2. State 1 can be the initial state, and state 2 can be the final state. Right, so you'll notice that as this happens, the path in which is taken by the system from one state to the other state is what we call a process. So if we are decreasing the volume of a gas by compressing the gas in a container, if we successfully manage to reduce the volume of a gas from volume 1 to volume 2, what is happening between volume 1 state to volume 2 state is what we call a process. Right. So if these processes remain constant based on a particular process, on a particular property, then if a property is held constant, as it moves from point A to point B, it becomes a process. So where pressure it remains constant, we call that process an isobaric process. Where temperature remains constant, we call that an isothermal process. Where the volume of a system remains constant, it becomes an isochoric process. Where the entropy of a system remains constant, we call it an isentropic process. Okay, let me take a look at the past examination paper. So for example, you will note that do we have a question here? Let me look for a question. I'm trying to look we have a question. Okay. I don't think it is in this past examination paper question. It's not in this. Okay, let me check if I've got something from the 20, right. So you may come across a question like this way saying A is compressed from an initial So A is compressed from an initial condition of 1 bar and 298.15 kelvins to a final state of 5 bar and 298.15 kelvins in a mechanically reversible process by cooling at constant pressure and heating at constant volume in a closed system. Assume A to be an ideal gas with molar volume of 0.02479 cubic meters per mole, and the constant heat capacity is CV is called 20.785 and CP is called 29.099 joules per mole per Kelvin. Calculate the final molar volume of A, the temperature of the A at the end of the cooling process, heat generated at the end of the cooling process, changes in the internal energy of each process. Okay, so basically what you need to understand is that as we look at this question, you will notice that there was change of pressure from 1 bar to 5 bar. But as this was happening in a system, the temperature of a system remained at 298.15 kelvins. So as you can see here, the temperature remains at 298.15 kelvins, right? And this is happening in a mechanically reversible process, first by cooling. So when cooling was being done, it means that the temperature had been lowered. But however, when cooling was being done, pressure had become constant. And then we also look at another dimension of heating where we are increasing the temperature, but we are heating at a constant volume, which means the volume of the system remains constant. So we have a closed system which is isochoric. We also have a closed system which is isobaric. We also have a closed system which is isothermal. in nature, or which is undergoing an isothermal process in nature. Okay, all right. The nitty-gritties of how to calculate these, to understand them and appreciate them as we proceed to address the first law of thermodynamics and the second law of thermodynamics. Okay, so bear this in mind that this is just an example I was just giving to all of us, right? Okay, so now, what do we mean by a process? To those who are struggling to follow, a process is where we are moving from initial step 1 to final step 2. So the path that is taken by a system to move from an initial step to a final step is what we call a process. But we also have what we call a cycle. Now, a cycle is a process with identical end states. So in this case, where we've got a PV diagram of a system, where we are comparing the pressure and the volume, we are simply saying that initially the volume of a system was at point number 1, and it changed to point number 2, which means there was a reduction in volume. So uh, the volume of a liquid or of a gas was compressed. So there was compression of a system there taking place, but afterwards there was a reversible process whereby it was allowed to expand again, returning to the initial state. So it moved uh, from uh, from state 2 back to state 1. So the first process was process A, and the second process was process B, and these identical states make the whole situation what we call a cycle. All right. Are we still together? If we are still together, then let me also give an overview of pressure and temperature. Giving an overview of pressure and temperature. So this week I'm just giving overviews, and we are appreciating certain elements and areas of thermodynamics concepts. All right. So if you are to look at pressure, uh, pressure can be calculated, and it has got different formulas in which you can calculate pressure. Generally, we say pressure is equal to rho GH, which is your gravity, your density times your height, and your density times your gravity times the height. It gives you the pressure. That is the general formula for calculating pressure. But our pressure is in different types. We've got gauge pressure, which can be measured. We also have absolute pressure. We also have atmospheric pressure. So absolute pressure can be determined. It can also be measured based on the knowledge of the gauge pressure. Atmospheric pressure, it can be calculated. It can also be set as a standard. So gauge pressure can be calculated as absolute pressure minus atmospheric pressure. And likewise, we also have what we call vacuum pressure. Vacuum pressure is calculated as atmospheric pressure minus absolute pressure. So the vacuum pressure is like negative value to the gauge pressure, or you will notice that many times the vacuum pressure is pressure which is calculated in a vacuum. So we can calculate this pressure underwater, while normally the gauge pressure is calculated above sea level. Though at times you may consider it when we do with calculating underwater as well. And we also have absolute pressure, which can be calculated as atmospheric pressure plus or minus gauge pressure, depending on the scenario that is at hand. So if you understand this formula, you'll be able to calculate anything with regard to pressure, depending on its scenario. Okay. maybe for us to appreciate, let me just give something that is interesting. Maybe if I may look from, right, we have this question from last year, which is a vacuum gauge indicates that the pressure of air in a closed chamber is 0.30 bar. The pressure of the surrounding atmosphere is equivalent to a 750 millimeters column of mercury. The density of mercury is 10.19 grams per cubic centimeters and the acceleration of gravity of 9.81 meters per second. Determine the absolute pressure in the chamber in bars. Okay, so what is required here is the absolute pressure. We are given that a vacuum gauge, that the pressure of an air in a closed chamber is 0.30 bar. So we've got a vacuum pressure here, which is the negative of gauge pressure, right? And we are also told that we've got the atmospheric pressure. The pressure of the surrounding atmosphere is equivalent to a 0 to 750 millimeters column of mercury. So we need to convert this 750 millimeters of column of mercury into bars first. Then we are able to calculate that particular pressure with relation to gravity using rho GH, there, and then we move on to determine the absolute pressure, which means absolute pressure is equal to atmospheric pressure plus or minus gauge pressure, right? So since our pressure is operating under a vacuum, you will just make absolute pressure the subject of the formula, which means absolute pressure, if you move it to the left side, it is atmospheric pressure minus vacuum pressure, and you have your answer in that regard. Are we together? Are we still together? So if you manage to answer in that context, yes, who has got a question? Okay, I think we seem to be on the same page. Just a moment. Okay, right. So if I may proceed, generally we can calculate our pressure using the formula rho GH, and the SI unit for that is in kilopascals. So we can calculate the pressure of a system. In this case, if you want to calculate the pressure of a gas as measured by a manometer, then we need to consider the height, we need to consider the gravity, we also need to consider the density of that particular gas, and we are good to go. So basically that's it for pressure. We are going to go deeper with relation to pressure. For example, if I may look at another example, maybe another example that we have here is the example of a pilot. Let me take this one, right? So it says the pilot of an airplane reaches the altitude 3,000 meters and the absolute pressure is 58 kilopascals when flying over a city. Calculate the local atmospheric pressure in that city in kilopascals and in millimeters of mercury. Take the densities of air and mercury to be 1.15 kilograms per cubic meter and 13,600 kilograms per cubic meter respectively. So already you are given the densities. You are also given the height, 3,000 meter here. You are also given the local atmospheric pressure, and you are also given the absolute pressure. And what you are required to calculate is the local atmospheric pressure, and you have the absolute pressure, and you need to calculate the gauge pressure. So in this case, you are told that the pilot is taking a reading at 3,000 meters level altitude, which is above sea level, and the absolute pressure is 58 kilopascals. So for us to determine our gauge pressure is equal to absolute pressure minus atmospheric pressure. And now that we want to determine the atmospheric pressure, we make atmospheric pressure the subject of the formula. P atmosphere is equal to absolute pressure minus gauge pressure. So based on the scenario that we have here, we have the absolute pressure and we are supposed to calculate the atmospheric pressure. So the gauge pressure, we can easily calculate it. We can easily calculate it using the given information on the density of the air and the density of the mercury. We can also use the height which we have been given here, since we can easily calculate our gauge, any pressure, including the gauge pressure, using the formula rho GH there. Okay. Are we still together? If you are still together, then I can proceed to highlight on pressure, on temperature. Yes. All right. So far it seems so far so good. All right. So if you are to look at temperature, you need to understand that our temperature exists in, it can be measured in degrees Celsius, it can be measured in kelvins, it can be measured in Fahrenheit, it can also be measured in Rankins. Okay, and therefore, by standard scientifically, we make our calculations usually in kelvins. We normally use kelvins for our calculation, though at times we can also use degrees Celsius. So in this particular scenario, we have absolute zero value for temperature. In degrees Celsius is minus 273.15, which is 0 degrees Celsius. So absolute zero, where we are saying that is 0 kelvins. When we are saying 0 kelvins, we are simply saying in degrees Celsius is minus 273.15, right? Degrees Celsius. But when we are at 273.15 kelvins, then our degrees Celsius will be 0 degrees Celsius. Likewise, if we are looking at Fahrenheit equivalent, the calculations here basically in kelvins is your temperature in degrees Celsius plus 273.15. And in Rankins is your temperature in Fahrenheit plus 459.69. And again, you can also calculate, convert from degrees Celsius to Fahrenheit. It should be your degrees Celsius in plus 32 plus 32 somewhere there. I'll have to double check. So you use these conversions, temperature conversions, to calculate the final temperature measurement. If you are saying that a thermometer was used to check the temperature of a baby and it happens to be so and so degrees Celsius, calculate this measurement in Fahrenheit or in Rankins. You simply take note of the degrees Celsius and add 273.15, and you have your measurement in kelvins. Okay, now when it comes to temperature variations, where temperature becomes different as you are moving from one temperature to a certain level of temperature, then the conversions will slightly differ in that as you move by any degree which is above zero, either by 1 Kelvin or 1 degree Celsius difference, if the temperature of a child was initially 36.9 degrees Celsius and it moves to 39.9, it means the change in degrees Celsius is 3 degrees, and therefore that temperature difference in kelvins is also 3 kelvins. And that temperature difference in and Rankines is 3 times 1.8 to have your value in Rankines. And that temperature difference in Fahrenheit is also 3 times 1.8 Fahrenheit. Let me give an illustration. Okay, we also have this situation where we are saying hyperthermia, which is an increase above normal body temperature, either by usually by 5, at least by 1 degree Celsius. So in this case, hyperthermia of 5 degrees Celsius is considered fatal. Express this fatal level of hyperthermia in kelvins, Fahrenheits, and Rankines. So it means that in kelvins is 5 kelvins. In Fahrenheit is 5 times 1.8, you get a value of what? If you calculate 5 times 1.8, you get what? If you have your calculator and say 5 times 1.8, you get 9. So in Fahrenheit, it's 9 Fahrenheit, degrees Fahrenheit. In Rankines, it's 9 degrees Rankines. That's the temperature difference there. Are we together? Okay. Now, if I may proceed, we can say if two bodies are in thermal equilibrium, two bodies can be said to be in thermal equilibrium when they have reached the same temperature, okay, that we now know. However, we have the zeroth law of thermodynamics, and it says if two bodies are in thermal equilibrium with a third body, they are also in thermal equilibrium with each other, okay? So they are in thermal equilibrium with each other. And so basically, if I may take a look at maybe in last, do we have anything from last year? Let me check if we've got anything respective or applying to last year. We may not have something in that regard or needing that application. But yes, here is the question, right? So it says, why is it that you can grab a hot wooden object and not get burnt, whereas if you grabbed a hot metal object at the same temperature, it would burn you? Okay, so in this case, it implies that we haven't been told that the temperature of your body is the same temperature of those two different objects. So in this case, to answer it, you need to understand that you answer it with respect to conductivity issues to do with heat transfer mechanisms. So this will be an issue of conductivity, that a hot metal object is able to conduct heat, whereas a wooden temperature is a poor conductor of heat. But in the situation where you don't feel any temperature difference, the zeroth law will roll into effect. Are we together? Okay. All right. Moving forward. We are going to look at different forms of energy. We are going to look at stored energy and transient energy. We are going to look at internal energy calculations. We are going to look at calculating potential energy. We are going to look at how do we calculate kinetic energy. We are going to look at how do we calculate chemical energy, and how do we calculate the nuclear energy of any system. In terms of transient energy, we are referring to heat and we are referring to work. And when we begin to look at heat and work, we have the first law of thermodynamics rolling into effect, which is what we know as the law of the conservation of energy, right? So basically, when we talk of transient energy, we are going to focus on heat transfer, where heat is the form of the energy that can be transferred from one system to the other as a result of temperature difference. And the science that deals with the determination of the rates of such energy transfer is what we call heat transfer. And so heat can be transferred by three mechanisms, which is conduction, convection, and radiation. And so we look at scenarios like a thermos flask. Why is it that a thermos flask is able to preserve hot water for a long time? It has to do with the issues to do with insulation. So there is no heat that is lost from this system through radiation means. Okay, but why is it that ukabata cup yetii yesimbi you get heat, you feel the heat is because of issues to do with conductivity there. And also it can be lost by radiation to the external environment in this regard. So heat flows in the direction of decreasing temperature. Okay, then if Katora can Coke, if you take a can of Coke, normally if it is coming from a freezer, you will note that it would have a certain temperature. Say it may be 5 degrees Celsius cold, right? But the moment you put it in a room with 25 degrees Celsius temperature, where the air is 25 degrees Celsius, you realize that there is heat transfer that is taking place towards the decreasing temperature, which means heat is transferred into this container. Okay, and we are going to explore how it happens in the various situations in this regard. Are we still together? Okay, so if you are still together, I'm going to give you an assignment for you to go and look at. This assignment is due on the 26th of April at 4 p.m. 26th of April will be Monday. It will be a Monday. So you need to go and look into this. I think by the 26th, which is in 10 days' time, would have been able to go through aspects of calculations in detail, calculations in terms of pressure, calculations in terms of temperature changes, calculations in terms of yeah, so this assignment is largely to do with pressure and conversions from one unit to the other. Here you can see an English unit, which is in pounds force there. So you need to express this and explain briefly why is that nose bleeding is a common experience at high altitudes, and why is that people tire more easily and experience breathing problems at high altitudes, and why is that people living at higher altitudes have adapted to the effect of high altitudes. And if you are to look at a car, why is it that a 2-liter car engine will act like a 1.7 liter car engine at an altitude of 1,500 meters? You need to have a thermodynamic explanation for this. And if you are to look at aeroplanes, for example, why do aeroplanes generally need a long runway at high altitudes? And why is that they have to climb to a very high altitude for cruising? So this is your assignment, which is due on Monday, the 26th of April. I'm going to send it both on the WhatsApp group platform as well on the Google Classroom. Do I have any questions today before we can call our lecture a day? Yes, Talent. Any questions so far?
Yes.
Catherine.
How are you going to submit the assignment?
You are going to submit it online.
Okay.
Yes. Any other person? Any other question? If there are no questions, ladies and gentlemen, I think we can call it a yes.
Say, are we going to type these calculations, or you write on paper and take pictures?
You are going to type.
Oh, okay.
Okay. If there are no any further questions, let us call it a day. You are allowed to exit. Thank you for
Sir,
your time. Yes, Brian.
tokumbirawo mutisenderawo assignment yacho paWhatsApp.
I already indicated so.
All right, thank you. But on the issue of typing this mathematics, zvinobuda bo.
Zvinogotadza nei?
Oh, let's hope so.
You can
Thank you,
type
sir.
it even on your phone unless your phone chiri chimbudzi.
It's a touch zvayo, but we'll just try.
If you have got a smartphone, then you need to install Microsoft Word or WordPress WPS. You can do anything on your phone.
Okay, thank you, sir.
Okay. All right, ladies and gentlemen, I am now stopping the recording, and I'll share with the group on Google Classroom as well as on WhatsApp the link to this lecture for the rest of our benefit so that we can play it over and over again. Thank you.